Welcome back for another deep dive with us. Today, we're going to be looking at something that's pretty technical, but really it's something that's impacting all of us in how we interact with technology these days, and that's large language models. You know, all those chatbots that are popping up everywhere.
Yeah, and we're talking about making those even better. The ones that are already huge, we're going to try to make them even better.
Okay, so my brain needs a little bit of a warm up here. Can you just remind us quickly how these LLMs actually work?
Sure. So think of it like creating a map. But instead of having like cities and roads, we have words and their meanings. And every word gets mapped to a point in this vast mathematical space. And its location is called an embedding. And that tells us about how that word relates to all the other words that the model knows.
So the more words, the richer the understanding of the language should be, kind of like a bigger dictionary, right?
You'd think so. But there's a catch. Just adding more words doesn't always make the model smarter. And in fact, sometimes it can backfire.
Really? So bigger isn't always better in the AI world. What's going on there?
Yeah, so the researchers in this paper we're looking at today found that with GPT-2 models, um, when they expanded the vocabulary from 32,000 words to 2 million words, it actually made it perform worse after a certain point.
Mm,
Imagine trying to learn a new language, but you only read like a children's book. You would only pick up a very small fraction of that language.
that makes sense. Yeah, it gets overwhelmed, doesn't it, by all the words that it doesn't really use and can't really grasp the meaning of. So what's the solution?
Well, this is where SCONE comes in. It's this new technique that's making a lot of noise in the AI world.
To scone, like the delicious pastry.
Like the pastry, yeah. But this SCONE stands for something a bit more complex. It's scalable, contextualized, offloaded n-gram embedding.
Wow, that's a mouthful. But I'm guessing the name gives us a few clues as to how it works. Can you break it down for us?
Absolutely. So instead of looking at single words in isolation, SCONE focuses on common phrases, or n-grams. So think about understanding the meaning of to be or not to be as a whole phrase rather than just understanding to be or not, individually.
So it's all about the context. How does that help the model learn better?
Yeah, so SCONE uses a separate model called the F-gram model. And this is specifically trained to understand these frequently used phrases. So think of it as like a superpowered phrase dictionary.
So like a dedicated phrase expert working alongside the main model.
Exactly. And here's the really clever part. These phrase embeddings are pre-computed and stored separately, like on a hard drive, rather than taking up space on these expensive specialized processors that run the main model.
So it's kind of like having a cheat sheet of pre-understood phrases that's ready to go without slowing down the main processing.
Precisely. And that's what makes SCONE so exciting. It enriches the model's understanding of language without creating this computational bottleneck.
Okay, so this all sounds great in theory, but does it actually work in practice?
That's the million-dollar question. And the researchers actually put SCONE to the test in a series of experiments. And what they found was really remarkable. So in one case, a model with SCONE actually outperformed a baseline model that was nearly twice its size.
Wow.
And it did so using only half the computational power.
So smaller and faster. That's amazing. How do they even measure this improvement?
They use something called perplexity, which is kind of like a confusion meter for the model. So the lower the perplexity, the less confused the model is, and the better its understanding of the language. They visualized this in Figure 1 of the paper, and you can clearly see that SCONE consistently had lower perplexity, which means it was making better predictions.
It's like Scone's helping the model to see the bigger picture and connect the dots better.
Exactly. And the researchers didn't stop there. They also discovered ways to fine-tune SCONE to make it even better, but we'll dive into that a little later.
This is fascinating. Before we move on, I'd love to know what excites you the most about Scone.
Well, what really excites me is that SCONE is tapping into something really fundamental about language. It's not just a random collection of words. It's full of structure and patterns. And by recognizing and utilizing these patterns, we can make AI so much more efficient and powerful.
It's like we're starting to unlock the secrets of how language actually works,
Yeah.
and then using that knowledge to create smarter machines. It's blowing my mind a little bit.
I know, right? And the best part is we're just getting started. There's so much more to explore.
Okay. Huh, wow. Okay, I'm catching my breath after that first part. It's amazing how much thought goes into making these language models work better. But I am curious about how do they even begin to train a model with all these phrases? The number of possible combinations must be just, I don't know, astronomical.
Yeah, you're absolutely right. The paper actually shows a visualization of this in Figure 3, and it's pretty striking. The number of unique phrases explodes as you consider longer and longer sequences of words. We're talking millions, even billions. It's like trying to catalog every possible sentence anyone could ever say.
So how does SCONE even deal with this avalanche of phrases? I mean, it can't possibly handle them all.
No, it's all about being smart with selection. SCONE focuses on the most frequent phrases, the ones that are most likely to be useful for understanding language. It's like finding the most valuable gems hidden amongst, a mountain of pebbles.
Oh, I like that. So it's not just about brute force, it's about finding the signal in the noise. But I'm wondering, how do they determine the best length for these phrases? Is there like an ideal length?
That's a great question, and the researchers actually experimented with that, and they found that going beyond a certain length didn't really improve performance. Figure 5 in the paper shows how the model's confusion level plateaus after a certain phrase length.
So there's a sweet spot. Too short and you miss important context, but too long and you're dealing with phrases that are so specific they might not be useful for general understanding.
Exactly, like Goldilocks finding the porridge that's just right.
Oh, I love that analogy. Okay, so we've talked about how SCONE selects and stores these phrases, but I'm wondering about the practical side of things. I mean, we're still talking about potentially billions of phrases. Doesn't that create storage issues?
Yeah, that's a valid concern, and the researchers address this directly. So they actually measured how much space these embeddings take up and how long it takes to retrieve them. And the good news is, even with billions of embeddings, they found that storage wasn't a bottleneck.
Oh, okay. So we don't have to worry about our computers bursting at the seams with phrase embeddings.
Not yet, at least. But it's definitely something to keep in mind as these language models continue to evolve.
Now, I read that they didn't just test SCONE on small-scale experiments, they actually scaled it up to a massive data set, something like 200 billion words.
That's right. And this is where those levers that we mentioned earlier really came into play. Remember, they could fine-tune SCONE by adjusting the number of cached embeddings and the power of that FGRAM model.
Right, like giving the model a bigger dictionary and a sharper mind. And I'm guessing those levers really boosted performance on this massive data set.
Absolutely. They tested SCONE on a variety of different text sources, including web pages, literature, forums, and even code. And it consistently outperformed the baseline model, sometimes even achieving better results with a smaller, more efficient model.
That's incredible. It really highlights the potential of SCONE, not just for language models, but for AI in general. We're seeing that sometimes it's not just about throwing more data and computing power at the problem. It's about finding smart, efficient solutions.
Couldn't agree more. Work smarter, not harder. Right. And that brings me to something that really struck me in the paper's discussion of related work.
Oh, I'm all ears. What stood out to you?
Well, they highlighted the challenges of simply scaling up the vocabulary size in traditional models. It turns out that after a certain point, bigger vocabularies actually lead to worse performance and increased computational costs.
That's kind of counterintuitive. I would have thought that more words always meant better understanding.
It seems logical, but there are a couple of reasons why it doesn't work that way. One is this issue of sparse updates. Imagine you have this massive vocabulary with millions of words, but your training data only contains a small fraction of those words.
So most of the words in that huge dictionary are rarely, if ever, used in the actual training material.
Exactly. It's like trying to learn a new language by only reading, a children's book. You're only exposed to a tiny subset of the language. And because these rare words aren't encountered often enough, their embeddings don't get updated and refined during training.
Oh, I see. So it's not just about having a big vocabulary, it's about how often those words are actually used and reinforced.
Precisely. And the researchers visualized this in Figure 9, showing how dramatically the percentage of words receiving updates drops as the vocabulary size increases.
So it's a balancing act. You need a large enough vocabulary to capture the richness of language, but not so large that it becomes unwieldy and inefficient.
Right. And that's why SCONE is so clever, by focusing on the most frequent phrases and pre-computing their embeddings. It avoids this pitfall.
Okay, so that's one reason why simply expanding the vocabulary doesn't always work. You mentioned there was another reason, right? Something about computational costs.
Yeah, so larger vocabularies mean larger embedding tables, and these require more memory and processing power. Think of it like trying to store an encyclopedia versus a dictionary. The encyclopedia is going to take up a lot more space. And the researchers showed this in Figure 10, how this memory usage just increases dramatically with vocabulary size.
So even if the model could theoretically handle a massive vocabulary, it might become practically impossible to actually train and run it because of the sheer computing resources required.
Exactly. And this is another area where SCONE shines. By offloading those pre-computed embeddings, it significantly reduces the computational burden on the main model.
So SCONE is not just about making AI smarter, it's about making it more practical and sustainable. It's finding that sweet spot between performance and efficiency.
Absolutely. And that leads to another fascinating point that they touch on in the paper, something called tokenization-free language models.
Tokenization free. I vaguely remember that term. Can you refresh my memory?
Sure. So currently, most language models rely on breaking down text into individual tokens, which could be words, parts of words, or even characters, before processing them. But tokenization-free models aim to bypass that step entirely and work with the raw text directly.
So instead of chopping up language into these bite-sized pieces, they're trying to understand the whole flow of text at once. That sounds incredibly complex.
It is. It's a very new area of research. And it raises some interesting questions about how a technique like SCONE might fit into this paradigm.
Yeah, because SCONE is all about pre-computing embeddings for these predefined phrases, which
Yeah.
are essentially tokens themselves.
Exactly.
Yeah.
It's not immediately obvious how you would apply SCONE to a model that doesn't use tokenization at all. But the core idea of SCONE, using this pre-computed information to enrich language understanding, is still potentially very relevant.
Yeah, it makes you wonder, are there like analogous structures in raw text that could be pre-computed and leveraged in a similar way? Maybe instead of phrases, you could look at common patterns of letters or even sounds.
That's a fantastic point. The researchers actually hinted at this in the paper, suggesting that future work could explore scaling embedding layers for other modalities, not just language.
So it's not just about making language models better, it's about finding new ways to represent and process information in a way that machines can understand. This research is opening up a whole new world of possibilities.
Yeah, it's amazing to think we might be on the verge of like a whole new era of AI,
Yeah.
where models can understand information in a much deeper, more intuitive way.
And it's thanks to these brilliant minds like the researchers behind SCONE, pushing the boundaries of what's possible.
Speaking of pushing boundaries, I remember one line from the paper really stuck with me. They wrote, "Future work could explore scaling embedding layers for other modalities." It's almost like a challenge to the whole AI community, isn't it? It is. They're basically saying, hey, we showed you how this works for language. Now go out there and see how it can be applied to other types of data. Imagine applying this approach to images or music or even scientific data. I mean, the possibilities are really mind-boggling.
It's like opening up a whole new toolbox for AI researchers. And the best part is this research is also addressing some of the practical challenges of AI, like energy consumption and computational cost.
Yeah, that's a really crucial point. As these AI models become more and more complex, we need to find ways to make them more sustainable. And SCONE is like a perfect example of how we can achieve both performance and efficiency. It's not just about making AI smarter, it's about making it smarter in a way that's responsible and sustainable for the planet.
Right. It's like we're learning to create AI that's not just powerful, but also mindful of its impact on the world.
Yeah, and that's a really encouraging thought. It means we're not just blindly chasing after bigger and faster models, but also considering the ethical and environmental implications of our creations.
This has been an incredible deep dive. I feel like I have a much better understanding now of how SCONE works and why it's such a big deal for the future of AI. But, beyond the technical details, what I find most exciting is the potential for this kind of research to really change the world. Imagine AI that can help us solve some of the biggest challenges that we face, like climate change, disease, poverty.
Yeah, I completely share your optimism. AI has the potential to be this incredible force for good in the world. And research like this that focuses on making AI smarter and more sustainable is paving the way for a brighter future.
So to our listeners out there, we hope this deep dive has, sparked your curiosity and maybe even inspired you to learn a little bit more about the amazing world of AI. It's a field that's constantly evolving, full of surprises and breakthroughs that have the potential to transform our lives in just countless ways.
Absolutely.
So until next time, keep exploring, keep learning, and keep asking those big questions. Who knows what incredible discoveries await us just around the corner? Thanks for joining us.
Thanks for having me.